those of you who missed Friday, we did health savings accounts. Um, it's anything's recorded. You're always welcome to go on and find it on Schoology, and you can take a look at it. But today, I will be in our packets. It says Algebra Review 2. And if you have the book, go into the book and find it. If you have the packet, go and find it. If you still need the packet because you lost the packet because, life happened, come see me and I'll get you a packet. Cool? All right. Hope you all are well. So, I guess important thing is, let's see, what should we do for a real life adventure on Friday this week? Let's rip apart the rent-to-own companies. You with me so far? Mm-hmm. Yeah, I'm sorry, I'm going to be a salesman in Friday's advertisement, trying to entertain you a little bit and kind of give you some perspectives on some of the big scams out there that are so easy to fall into and you don't want to. All right. So I'm going to do some notes on, we have two different things that we're looking at. They both could use Desmos very easily. But let's do something simplistic. Let's say we had a graph that looks something like this. And all I'm going to look at, and I'm just making this up, let's say that this is the point -5, 0. Let's say this is the point 2, 0. And let's say this is the point 6, 0. Okay? I don't know what this equation is. It's just some arbitrary equation or some arbitrary graph. What are some things, just by looking at it, everyone agree it crosses the x-axis 3 times? Yeah. I'm not really too concerned that it crosses the y-axis because most things that we graph in math will cross the y-axis. So I'm not too concerned about that, but I'm just concerned about the x-axis. Okay? So what I'm going to do is I'm going to draw myself kind of a number line. Okay, this is not part of the graph. I'm making it a different color for a reason. And I'm going to put the point -5 on there. I'm going to put 2 on there. And I'm going to put 6 on there. Okay? Still following me? A couple other things that I'm going to note on this graph, and these are just made up values. Let's say this is the point -1, 3. And let's say this is the point 3, -1. Okay, so I have a maximum, I have a minimum. They're called local maxes or local mins because they're part of the graph. They're not the end behaviors. Okay, so I'm also going to put -1 here, and I'm going to put 3 here. Okay, so those are all pivotal points to this graph. Okay, so I want to do something that sometimes will make a lot of sense. Sometimes you're like, wait a minute, where did that just come from? So over here, I'm going to do this. I'm going to do this. And I'm going to do this. Okay. So, what does it mean? Those are positive values versus negative values and positive values. So what do you think? Where is this positive coming from? Where does this negative come from? Where does this positive come from? Where do you think? Any ideas? Yeah.
If the graph's going up, it's positive. If the graph's going down, it's negative.
I like it. The graph is going up, it's positive. If the graph is going down, it's negative. Okay. So let's take this a little step further. I love what you're saying because you're exactly right in your conversation on that. All right, let's do, purple's fun. So I'm going to draw something called a tangent line a whole bunch of times. Okay, these are called tangent lines. Those purple are tangent lines. And what a tangent line is, by definition in geometry, a line that's tangent to something touches a graph once. It's a line that touches it once. It's tangent to it. Now you're like, yeah, but I thought tangent was opposite over adjacent. It is when you're dealing with triangles. And it also relates back to this, but I have these tangent lines. But we have these tangent lines that as we go through this, we can create all of these tangent lines which can and will touch our graph one or more times. So this tangent line touches here once, touches here once. Let's pretend that one touched. We have all these different places that these tangent lines are touching once. Okay? Still with me? Okay. So that's kind of the first thing. Yeah.
On one of them, if you continue the line, it would hit. Does that matter, or can it be like a line segment, I guess?
Yeah. Yes. Well, it's called the instantaneous velocity is what we're looking for. And that means that exactly at that point, if we had a tangent line, we ignore everything else about the graph. At that exact, what would the slope of the line would be? So this is dealing with slopes of tangent lines. Okay, so that's kind of the first thing to think about. So if we come across something that we want to create something called a sine line, that has to refer to the slope. And when I say slope, we're literally talking about algebra 1, y2 minus y1 over x2 minus x1. Remember, in algebra 1, you gave you 2 points, labial points, maybe you label them x1, y1, x2, y2. You find the slope using the slope equation. Then you use point slope, plug it in, distribute over, and solve for m, or solve for y to get y equals mx plus b. Does that kind of ring a bell from that 4 years ago, 3 years ago maybe? Okay. All right, so that's kind of the first thing we're going to touch upon. But what if we had something like this? Okay. Now we want to set up kind of a sine line to this as well. So I'm going to draw myself a horizontal line. And if I go x plus 2 equals 0, so x equals negative 2, and x minus 7 equals 0, so x equals 7. Are you following my math?
Yeah.
Pretty simple. So I got negative 2 here. I got 7 here. Okay? Yeah, in between our other numbers, of course. I don't have to go plug the 0 and the negative 1 and the 1, 2, 3, 4, 5, 6, things like that. It's not necessary. We're just going to plug those in. What does this really mean? Greater than 0. What does greater than 0 mean as far as positive or negative?
Positive.
Okay. So this means positive. I'll squeeze in there, positive. That's supposed to say positive. Let's pretend I can squeeze things in nicely. Okay, so things are positive. Okay, I want to know where this is greater than 0. So I'm going to go forward for a second. So that was x times a quantity, or x as a part of a quantity and x part of a quantity, which means it's going to be x squared. X squared somehow forms a parabola. Okay, a parabola can indeed open up or down. Yes, it can open sideways, but we're not going to deal with sideways parabolas at this point. We're just dealing with the way things open up or down. If I have x squared, it opens up. If I have negative x squared, it opens down. That makes sense so far?
Mm-hmm.
So continuing a little bit more with this, if I drew in this, where these two values cross the x-axis, there's a portion of the graph that's positive, there's a portion of the graph that's negative, there's a portion of the graph that's positive. Now, that does not mean that's what the slopes are. That just means where it's above or below the x-axis. So positive would mean above the x-axis, and negative means below. the x-axis, which all in turn means y values. And y values in math, we use the term f at x. That's the same thing. That's functional notation. What kind of y values we're going to get. Now, if I go exactly at this point here or at this point here, it's not positive or negative because the y value exactly at those two intersection points is 0. 0 is not a positive or negative number. Okay, I know some people try and argue it going, yeah, but 2, 4, 6, 8, those are even numbers. And it's like, right, and then 1, 3, 5, 7 are odd numbers. Yeah, you're right. How can 0 not be positive or negative? Anybody know when and where and what peoples figured out the concept of 0? Okay, Roman numerals. The Romans didn't figure it out with Roman numerals. Yeah, what do you think?
The Arabic number system?
Nope. For them. The ancient Aztecs came up with the concept of 0, concept of nothing. I'm going to give you 5 of this. I take all 5 of those things away. You now have none of that. Okay? I kid you not. It comes from ancient Aztecs had developed it, which is, just cross-curricular little history lesson for you. Okay, so let's go back to the question I had here. Okay, how can we approach this problem to fill out this line here? Well, friends, I think what we want to do is realize what a few things are. This is positive, so that's above the x-axis. And yeah, we could go and graph stuff by hand because we're sick and demented and twisted people, or we have a friend named Desmos that we can use. All right. Oh, we already had Desmos over here. All right, so start graphing. Think about it. All right, so I'm going to go y equals. Okay, so I'm cheating the system. I'm going to do y equals. We had it greater than 0 in this case. Greater than 0 meant it's above the x-axis. I had x plus 2 and x minus 7. X plus 2 and x minus 7. Okay, so let's darken this a little bit for us so we can kind of get a look at it. So we have this point here and this point here. I could zoom out a little bit so I could see the whole parabola. Let's get these points back labeled. Okay, so we want to talk about where this is above the x-axis because it was greater than 0. So does everyone feel comfortable from here up and from here up? It's above it?
Yep.
So in between those two, it's below it? Okay. So we want to use something called interval notation to describe it. And we describe in the x direction what's taking place with the y. And that's sometimes a harder concept to grab onto. What's taking place in the x direction that makes the y do something. Okay? So from -2 to 7, or between -2 and 7 in the x direction, it's below the x-axis. Everywhere else, it's above the x-axis. Okay? So this means it's above the x-axis here. It's above the x-axis here. Okay? So let's, using this sign line, talk about something called interval notation. Which is in the x direction. Okay? Where is this arrow pointing to? Yeah, which infinity? Negative infinity. And where is this arrow pointing to? Positive infinity. Okay? So we're going to use the infinities to describe where this is positive, where it is above the x-axis. So from negative infinity up until -2, and it's going to be a soft bracket. Soft bracket means I'm not going to include the -2. If it was a square bracket, which we call a hard bracket, that means I include that point. And then it's also above the x-axis from 7 to infinity. So the solution to our problem to answer this question is negative infinity to negative 2 and from 7 to infinity. Yeah.
But the negative infinity to negative 2 is smaller than 2.
Do what?
But the negative infinity to negative 2 is smaller than 2.
But our graph in the y direction is continuing to go up.
Oh, okay.
Okay, so here, let's go back to Desmos and just take a quick glance. On our graph, if I go from negative 2 and I continue to go this way,
Yeah.
where's my graph going? It keeps going up higher, 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 higher. And from 7 to infinity this way, the graph is continuing to go up. So we're getting bigger and bigger and bigger y values.
Yeah.
Okay? So that's kind of the first thing. One, getting used to Desmos, realizing where it's going to work. If I flip my interval over and made it less than 0, that means I have negative numbers. So let's go back to my original, and let's just change the problem to this. X plus 2, x minus 7. Where is it less than 0? This means it's negative. And if you look at our graph, the interval notation, I period n, goes from negative 2 to 7. And they're both round brackets because below the x-axis is a negative number. Right on the x-axis is 0. So, and you have to be cautious. If you had this or this, we might have to start using square brackets. But a square bracket can't be used when you are on infinities. So that's kind of the first thing I want to look at. Okay? So we're going to see some of that. The second thing I want to look at is on the backside, so 16 through 21, we have some stuff that is raised to an exponent. So let's take a look at, say, number 16. Okay? Number 16 on the backside of review algebra review 2, algebra review 2, or whatever it's called. But number 16 says this. Now, they say, hey, we can use logarithms to solve this. And that's great. I'd go log. If I do a log, that brings the exponent down in front of the log. Then I deal with this log. So I get basically x minus 1 log 5 equals 3x plus 5 log 5. You can cancel out the log 5s. So then you get x minus 1 equals 3x plus 5. So it solves very simply for you. But I want to show you where Desmos is going to be our friend here. So I'm going to take each of these equations and make them their own equation. And I'm going to try and figure out where these are going to intersect each other. When they intersect each other, we're looking for the x value only. Okay? All right. So I want to graph both of these on Desmos. So if I go on Desmos and get rid of our graph, I'm going to do my first graph. I'm going to go y equals 5 parentheses. Notice how it stays up, and I think I can go x minus 1. Oops, I need to put it in parentheses. X minus 1. Okay, so that's what the first graph looks like. And the graph itself isn't that significant to know. It's just, hey, we have something we graphed. We graphed the left side. So now I can graph my right side. And so I get 5 raised to the parentheses 3x plus 5. So notice we have a green graph and we have a blue graph. Okay, I could zoom out and you have these two graphs that go along the x-axis and then they shoot straight up. But something takes place, and we're going to zoom in as close as we can in here. -4, I believe. There we go. Let's see. Zoom in a little bit more. All right, so hang on. Let me just solve this real quick. I didn't do it in my head. Sorry, I'm broken. Okay, so at -3, something's taking place. So I'm going to keep zooming into this -3 as long as Desmos will allow us to do it.
Why don't you just tap on it instead so it can save you there?
Because I want to get the exact value. There we go.
But even if
We're
you
still
zoom
off.
out, wherever it crosses, it'll just put a dot there, even if you're super zoomed out.
Will it?
Yeah.
Did it? What'd you get it exactly?
-3, 0.0017.
Cool. All right. So let's take it back to home. So you're saying if I just tapped at -3 right here?
Yeah.
Cool.
Oh.
Roughly?
Yeah.
So what did I say we're looking for as far as the answer? Which value?
The X.
The X. So -3 is the solution to this problem. Okay, and I was trying to zoom it in because I wanted to try and see if I could get close enough to see the change of one over the other, but it wasn't working on Desmos. Sorry, Desmos failed you. So when I go to try and find it, now notice this, if I go click over here, it's going to give me like values, but like I could highlight, hold it there, but it's not going to stay. But this one stayed because this is finding these exact intersection of these two lines. So on that first problem where I solved it, or I had put it, this says that x equals -3 is our solution. Now, we could solve this because I have the same exact bases. The algebra way of solving it would be doing this. Subtract x from both sides. Subtract 5 from both sides. So I get x equals -3. So that checks with what Desmos found us. You're like, well, Stirp, why didn't you just solve it that way? You're right. Why didn't I? Because I wanted to show you a basic foundation of how to do it. So from here on out, when you have something equal to something else, so you have smiley face equals frowny face, you're going to go y equals smiley face, and x, or excuse me, not x, and y equals frowny face, and where in the x direction, there's going to be an x comma y value that it works at, but we're just concerned about the x value as the answer. So Desmos is a pretty powerful tool for you in solving a lot of these types of problems. Okay, so I want to give you guys a lot of time because if you get it done, because we're having a snow day tomorrow, because, you know, Stirrup said so, this will prevent you from having to shovel snow for your folks. Okay? Hey, go shovel snow. I got math. But you're going to get it done in class and they're never going to know, right? All right, so I would like us to work on algebra review number 2. I want you to do 13 through 21. And Desmos, honestly, could be your best friend. 13, 14, and 15, I want the interval notation for the answer. And then 16 through 21, because you're using Desmos, you could just say x is equal to whatever the answer is. Got it? Cool? Giddy up? Yeah. Yeah. And save